This information is brought to you by Charles Sturt University.
Proving stuff. So what I want to do is I want to move on to the second part of chapter 1, which is looking at logic. Logic's really important because at the heart of it, that's what computers are all about. They really are just a bunch of zeros and ones at the heart of it, and just trying to work out how to process zeros and ones. And you can think of that really as being just a bunch of logic gates. And is that how you approach it in ITC 161? Yeah. And so just understanding what logic's about, and that's true at the very base level, of which most of you will probably be blessed never to actually have to deal with very much. But it's also true at the high level. So if you're writing a computer program, you have to write true and false statements all the time. So every for loops, if statements, etc. It's really common just for branching and etc. That's going to and repeating. That's what you have to do. And so understanding that sort of logic is important. So that's in terms of actually utilising the computer. But it's true for other things too, and that's in terms of mathematics. And that you need to be able to prove things. That's true just for mathematics in general, but whenever you're dealing with things that are mathematical, like an algorithm, you have to understand the idea of proof. So I want to cover the idea of logic, but I want to spend more time about thinking about how can you use logic to prove various stuff. So thinking about what a proof means. You have done quite a few already. You've done a few already today, but just want to think what the best different strategies are to think through that. Okay, so just some lingo when it comes to logic, and so for example, where lots of these words come in is there's a computer program called Prolog, which is basically a way of
Did I hear an audible sigh?
It's not a fun language to work in.
All languages have their pros and cons. The benefit of Prolog is it can deal with simple and complicated logic for you.
Prolog is first syllable. The only Prolog is first syllable.
Yes. That's it.
So I vaguely remember doing it when I was an undergraduate, but it's the only time I think I've touched it directly. But you can use it for key artificial intelligence. So the languages that are the most popular, as you've worked out, are the procedural ones, or ones based on that, because it is more akin to perhaps how you might think about algorithms. But people have defined computer languages differently based on different ways of thinking about stuff. Prolog's an example of that. So the heart of logic is just having true and false statements. So I just give a name for these true false statements, call them a proposition. So it's something that it can be true or false, very clearly one or the other. And you see them all the time in computer code. So if do the pseudocode. So the true false statement in that particular code there is the character Y or not? So is the answer yes, effectively.
What? And it's not Y? It's not Y.
Let's look at it, sorry. A here's the variable, Y in quotation marks would be a character. Sorry. Let's just pause for a sec. In the room here, who knows how to do computer programming?
I mean, I know
all the computer science students should have done some basic Python. Python's balls.
I was just messing around with Snake the whole time.
Python has a reasonable market share, believe it or not.
It's a terrible language to learn the basics with, because it's
would you prefer C++ or something like
what
that?
you learn in Python isn't very transferable to other languages.
It's really good about it's about encouraging good style, because the indentation's like, I don't know.
That's literally what they said. The only reason we're doing it is to teach us good style and conventions.
Who hasn't done computer programming? You've got no idea what it's about at all. Okay. So no one's prepared to admit it. It's good just to, I'm presuming most people have, but if not, I'd like to know just so I can make sure that I'm not going to alienate that person for the rest of the semester. It isn't quite true, but I would like to make sure that I include all people. So computer programming is very much the forethought in here because that's where most you like to have some touching on programming, I presume, or at least work with people who do the programming for you. Maybe it's your guy, I don't know, but you need at least to have some understanding. So proposition, just a true or false statement. This is another English sentence. This is not a proposition. Why not?
Because it's a paradox.
Okay.
Let's go with that. I'm going to go with yes for that one. Yeah, that's true.
It's a yes from me.
Yes. Yeah.
So it's a paradox is the correct answer. So it's one of these stupid things that cannot be either true or false. So if it was false, and then that would imply the sentence is true, which can't be possible. And if it is true, that would imply the sentence is false, which is also not as well. So that's not a proposition. We don't like those things.
I know how to fix it. You just put a question mark at the end of it. Is that this false?
Okay. So that's a proposition. We can have compound propositions, which basically a way of chucking lots of things together using lots of the key operations. The common logical operations that you'll encounter, and have encountered on, I suspect, will be and or not. There are other ones in existence. So they're common logical operators. And so that's one example. So compound just means chucking a few together using the and or nots. And there's no ors in this particular one. But this one means not some proposition and some other proposition. That's what it pretty much says. Who cares what the actual things say in there. So compound proposition, just a bunch of things chucked together. So a way of understanding logic is many ways. You can understand it just like we did the set theory is a bunch of properties to simplify things down. That is useful, it is. I'll often have practical ways to do with truth tables. So how much of this stuff have you done before?
161 we did truth tables.
Okay. So what are the different logical operators? So I want you to tell me the answers here. So this will make a revision then, if you know. So the key so truth tables, you can write truth tables in true and false. Since we're dealing with computers, I much prefer binary. I tend to write down truth tables like this, so P, Q is being that sort of stuff. Just some things with truth tables. You think the sensible thing to do would be just to write down the zeros and ones in a systematic order like there is here. People, you can also use grey code. Did you do that one?
Grey code what?
So grey code is writing in a different order where you change one bit at a time, which is useful for simplifying stuff. Well, I'll mention it again at the end of the session called when we do Carnot map. So it's useful not to always do that order. Don't be wedded to that one, but we'll stick with that because it's just nice, simple to begin with, and because I suspect that's how you've already seen it. So we have different key logical operators. Let's do P and Q to begin with. So P and Q, there's nothing wrong with writing that down. People who define this logic like being super brief, and so they use like a V symbol.
PVQ.
True.
Sounds like a very interesting.
It's upside down. It's an upside down V, which we call it a wedge. So P wedge Q.
P upside down V Q.
Yep. So and don't try to read it as some upside down V. Just read it as the word and. Okay. So people who define these logic, they like super briefness. So
all maths people like briefness though.
So I'm happy if you're ever writing any stuff down, use English words. Nothing wrong with that. So if you, depending on computer programs, some computer programmers like Python, they actually use the word and, but others use other symbols like an ampersand, for example. So some people in computer science do the same thing. They're also guilty of abbreviating it sometimes, and it's different depending on the language, which confuses you if you're doing one changing.
There we go.
So that's P and Q. what's the truth table for it? So if you do, what's 0 and 0?
0, 0, 0, 1.
So 0, 0, 0, 1.
Good job.
I did. Oh, could I pass the course?
Yeah.
Oh, nice.
So the other common one is OR, which is P looking like a B symbol.
We're here to use that brain, bro.
That's a abbreviated form.
Sure about this? Everything you
It's basically, they correspond to the unions and intersection symbols, just with a point at the top, as the case may be. Okay, what's the truth table for OR?
0, 1, 1, 1.
0. So, at least one person knows it. I hope everyone else does. So, that corresponds to the inclusive OR. Just reminding everybody.
Is there an XOR one?
There's an exclusive.
Yeah.
So,
What's the symbol for that, though?
because I don't use it very much,
It's just an exclusive. Oh, that's boring.
that's it. And what does that look like, just out of curiosity?
0, 1, 1, 0.
Okay. So they're the and or it's the critical ones. What else we need to know? So let's just do one more. Let's do not P, and in terms of symbols,
Exclamation mark is one, along with a dash on top.
or a squiggly line, or a tilde. Yes, I know. So you can see it.
Too many.
So that's how the way we're going to. The way I'll do it I'll just copy what the done is in the study guide.
That's the easiest way to type it.
Oh man, what
There's a little minus sign in front of it, so to
what alt
speak.
keys do I have to press for that? Alt 3052.
Alt 0137.
Yeah.
So I use a typesetting program called LaTeX, and it's /neg. No, this is not Word. I use Word.
Terrible.
So LaTeX was written by a guy called Knuth, who did lots of algorithms sort of stuff.
Microsoft Mathematics would have that? Reckon Microsoft Mathematics would have that?
Yeah, so the latest Microsoft realises LaTeX is in existence. So if you just do /neg, it would produce the same symbol.
Cool.
So it's sort of a not P. What's the truth table for not P?
Oh, 1, 0.
You just have it up.
Yeah, it was, but if you could just do it, could have revised it. So they're the key truth table. So two statements are logically equivalent if they have the same truth tables, essentially. How do you prove things using truth tables? Why don't you have a go? Let's do revision. Why don't you do this exercise? Is that all right? So at the top of the page, I've got two different logic expressions. The first one is, let's read it out. So this one is P and not Q. So these for or. Yes, I got it wrong last time. So P or not Q. Thank you. And the other side is not of, not P and Q. It really is an application to Morgan's law, disguise. So I want to prove these two things are the same. You can prove it more than one way. You can prove it using the rules of logic, which would be Morgan's law, just use the Morgan's law to expand it, and that's it. You can prove it using truth tables, and that would be basically draw the truth table up for both the left-hand side and the right-hand side separately, and show the truth tables match up. And if you're not told which way, you can choose whatever way you want to do it. So you've done the truth tables way, I gather, from 161. So you want to try. So have a go at try writing it down. So the way I think to do it is to write the truth table for P and Q, and for not P and not Q down, because we're just going to use them readily. So it's useful just to have them there to begin with. And then two sections, I'll do the left-hand side here, and then I'll do the right-hand side. So just in two different sections. And I'll put as many middles, compound, any intermediate results or down as I need to, essentially. So for the left-hand side, what would you pick an intermediate step, or you just go to the end one straight away?
You've got all the info you need already.
Yeah. So you pretty much got all the information you need already. So you probably just need to just fill it in as it is. So I just write down. Let me write on the screen here. So I'd write down the expression for the left-hand side just there, and then fill out the rest of the truth table. You can do that in a second. For the right-hand side, what would you do?
Let's do the brackets and then do the not bit afterwards.
So do the bit in the middle first. So you put another column in, and then do the not of that part. And what you're hoping is that these two columns here will have the same. If they are, bang, that means they're proved by the truth table. If not, they're not the same. Yep.
Still write them with just the pair with the line above it rather than with the line next to it.
Yeah, I mean, I understand what you're talking about.
Yeah.
So, I mean, you might find it easy just to use the words. So you might just say P and Q and not P. Oh, that might be easier still. The overline is clear. We'll use that notation in lots of other cases to mean not. So I know exactly what you're talking about. So there we go. See if you can fill the rest of it, the table in. You can tell me the answers in a second. So, waiting for pens to stop. The ones working on the paste paper more than the ones in the air.
Conspiracy.
So, what have people got down for the first column? So, P or not Q. So 1 1 0 1. Yep. And then the other case is not P and Q. 0 0 1 0. And if you take the not of that, it just means flopping zeros and one around. Flipping them around. So flop different. And that would be that would be my answer. And so you should make it clear what particular columns are you supposed to be comparing with, and then write a conclusion down like I've got at the bottom here, and you say because the two bolded columns are the same, that implies the left-hand side and the right-hand side have the same truth table. There must be logical statements. So it's not just. I don't want you just to write a table on the piece of paper. I want you to explain to someone else what it means, which can be really straightforward, like one simple sentence. But you need to. But maths, like lots of other things, is about communicating to other people. It's an idea to be able to explain what it is. And English words are are really important for that. Let's have a break for 5 minutes. Here's a bunch of logic expressions you can see on the screen over there.
I hate logic.
PPP.
What? So the challenge for you to begin with is remembering what all these symbols mean. Once you get over that, I'm sure you can come at the answer. So what's the first one there?
It's just P.
So it means not P, which is P. The next one.
P and not P, so it's going to be 0 or 5.
Or false, if you think of true and false statements. So, and in terms of binary, often think of false as just being 0. So Python would force you to think of it as being false, but so 0 is common for most languages. Next one.
It's always true.
So it's P or not P, and that's always true. That's true. True or 1, think of that way. Next one here.
P and true.
Playlist terrain.
So P and true.
That should just be P on its own.
So the true or falseness of that statement just really depends what P is. That's the answer to P. Next one long.
P and
0 equals 0.
Oh, get around the wrong one. So P or
true would be
P or true.
0 equals 0.
Would be true.
Let me get these things out.
What is going on right now?
P and true.
What is going on here?
Okay.
That's your screenshot.
So,
Oh my god, what the hell?
There we go.
Understood there for like a solid 5 minutes.
Oh,
Looking at all.
Oh, my brain. It's okay.
That lag on the
Oh,
screen.
yeah. No, I feel that's therapeutic.
It's not. It's like
Skype screen
it's skipping the actual. It's skipping the actual movement. It's just instantly doing it, like straight up, bam.
Yes, and it's very fast.
okay. Next one here. So they're the ones we said. This one's P.
Or true, so it'll be true.
P or true.
Can we call for an emergency break? There's a Bulbasaur nearby. Wait, you're serious? No.
Yeah, then the Bulbasaur.
Wait.
See, now everyone's freaking out. I shouldn't have said it.
No.
So that'll be not P.
There was a joke.
So,
That pen right now.
okay, so thank you. You've been really good at the answers, but I want to force other people to think about it too. So,
Java expert needs to shut up.
so this one is P. So again, you have to just think what it means. So P and false. So it doesn't really matter what P is at all. It's always going to be false because of the and false part. This one is P or false. And when you think or false, the or false means doesn't tell you anything at all. So the true and false really just depends on the first statement. So it's going to be P and the last one, P and true.
I'm ordering a
It's P.
Terrible.
And so because of those two statements there, then if you've got a bunch of and statements, a bunch of or statements, if you know if it's true or false already, so you've got a bunch of or statements, you already know it's true, there's no point looking at the rest of the statement because you know it's going to be true automatically. And so some computer languages do short-circuiting logic statements where as soon as they know it's true, they go, that's it, I'm bailing out, don't have to do anything more. Which saves a bit of saves a small amount of computing time sometimes. And depends how you're coding, sometimes that doesn't achieve what you want it to be.
Like you could just say for an example, sorry, just real life example, in Java, when you're checking if something's not null, you can like do if P is not null and if P is something, if it sees that it's null, then it's just going to exit straight out.
Yeah, and if it didn't do that, that means if it was null, it would say it's true automatically, but then the next part would give an error.
Yeah.
And so that short circuit logic, as it's called, is really handy in many situations. The only time it wouldn't be useful is when you're doing something with C++, if you want to use the logic statement to increment things at the same time to be really fancy. But you often kill yourself doing those sort of things. Yeah. As in.
C++ is just like getting phased out because it's not very useful these days.
It's inspired lots of other things though. So at the end of the day, back to this stuff here, you need to understand what the symbols mean, and then just think through the implications of it all. Okay. So just like for sets, we can come up with a bunch of algebraic properties for propositions, for true and false stuff. And the rules are exactly the same, just translated to different language, essentially. And so they all are here. So same words, etc. Just different symbols. The way to remember them is to go look at the formula sheet again, and the first column I've got here is all the set stuff. The exact same rules here are for the logic. And so what we use them in practice is the same sort of stuff. So if I remind myself what I've got there.
It's very hard to level up now. You need a lot of speed.
Oh, the noise again.
So I want to do... I can't stop it. So this one here, this is a logic statement. So just reading out loud. This is P or
P and Q.
P and Q. So what I want to do is I want to try to get the most simplified version of this. So I want to do a bunch of rules. So I want to do a bunch of rules to try to simplify it down. And if you think through what it means, you might be able to work out the answer. So what some people were just whispering, that's fine. I'll work it out loud because I want you to try and engage it yourself. So you're trying to think, how can you use some rules to simplify it down?
Doesn't really matter what Q is, because it doesn't really.
So what's your approach? What's your thinking with it? So a good idea, I think, is just to get a sense of what the answer is going to be. And it's some below over there, middle row. What is the answer going to be? P. So you can try to go, I think it's P. How could you prove it's P then? If you've got no idea, you can always fall back to truth tables.
Well, if P is true, then it's going to be true or true and something else. So it's just going to be true on its own, like P on its own.
Yeah, because there's an or, the P and Q actually don't matter.
Yeah, exactly.
Okay.
P is also in the next, like in the order.
So if you start thinking about it, because you've got P or something or other, so let's just give some names for it. Let's make, this is just an example just to give a sense of what it might be. Let's just say P is a proposition of being a car. So either something's a car or it's not a car, right? It's true or false.
Yeah.
Q is the colour, green. So if something's either green or not green, so true or false. So this sort of saying is something like do you have a car or a green car? That's sort of the corresponding expression. So P and Q be green and car, so green car.
Green and car is already a car as well.
That's right. So when you've got this sort of expression, you're saying, I've got a car or a green car. Well, green car is something more precise than a car. So it really just matters if you've got a car or not. So if you've got a car, both of them are true. If it's not a car, both are false. If it's a green car, well, it's a car, so they'll both be true. So at the end of the day, this is just saying you've got a general condition and something more precise than it. So it's really only the general condition that's going to make it any big deal at all. So like we're saying, we're going to think it's going to be equal to P. Now that waving my hands is not really a proof just yet. How are we going to try to prove it? But that understanding of it might help us. So these are some steps to do that sort of stuff. And that is, we really want to say is, well, there's a bunch of it's really just want to factorise the P out, and it's really just being able to say that the Q and falses can go by itself. So I want to factorise a P and out. So I'm going to manufacture it. I'll put something in here in a second to try to make it not really about P, I'm just going to try to make it about Q's and trues and false stuff. So, and why I'm doing this, I've got to give it a name here a second. I want to factorise this P or bit out, the front of it, of something and Q. And it's something that dots there is either going to be true or false, one of the two of them. I can go from that.
Green card.
So why I'm doing this particular way is whatever's here is, this probably really is about the fact that when you've got a time of true, it just absorbs any other expression whatsoever. That's what it really comes down to. So let's just go back. When I've got this expression here, I've got to think of one property. So what I've really done here is I've written P as P or something. P and something, sorry, P and something. So P and what gives me just P by itself.
True and true.
P and true. So I'm going to put a true in there. And you know, well, what result is that? So you just go, well, we did it a second ago. So P and true equals P. One of them just listed there. Just find it. And just find the name. That's one of the identity rules. So now you know what the rules, you know what most of them are. You just need to know look at the names when you need them. So that's the identity rule. Now we've put that in, it then allows us to factorise it out. And when we do the factorising out, see there, that factorising
420 off.
Oh no.
Blaze it.
is a distributive rule. You easily amused.
That means I need to distribute my blazing material, does it?
Yep.
Your vapes, yeah.
Precisely.
Distributive is just another way of saying expanding brackets, really, and we're using it the opposite way here. It's factorising.
Should say vapes.
Sorry?
It's distributive actually means pass the dutch.
So now we've got
Every single mass lecture in this
let me factorise it properly, and that might be better. I'm just reading through my own writing here. So I factorise, what I did is I factorised this P and out, you see that's out, and I've just written what's left in here. That's what I've done after I factorised it.
So true or something is true.
And so, the true or Q is just true. So that idea of true absorbing the Q along, that's really the heart of this. This heart of this property is really that true absorbs anything else. So this overall property is called the absorption property because really the P is absorbing the other term. So the general condition absorbs the more special condition. We know with words. So this one here, when T or Q is just down a Q, really that's one of the special properties of being true. That's what just trueness is about. And again, you can look it up. So it's one of those rules there, such a special property. And the last one, if you've got P and true,
True is just P.
it just reads the P, which is one of those identity rules again. Which is what we started with as a matter of fact. So that's one way of proving it. That one is, so out of all the things to prove, that's one of the harder ones you could do, I might add. So lots of the ones I might give using algebra properties would be not as hard as that.
Bye-bye.
Everything's taken totally.
And the reason why that one particularly is difficult is just that very first step is actually making it more complicated briefly, and that's the hardest thing is to realise those sort of things. So if I was to give you that sort of one, I would give you a big hint to tell you that's a good place to start. Okay.
I mean, it's so. It's like so.
Okay, so I want to talk about other sort of logical operators which have benefits what I'm talking about. Can you guys be quiet, please? Okay, so in terms of computer programming and or not are the ones you're going to see lots of the time, but we want to deal with some other ones. So another one I want to talk about is implication. So I want to talk about P implies Q. And it's really, so it's useful in logic. So things like if you're trying to do artificial intelligence with logic, sometimes it's useful. So if you want to write a program that can solve one of those logic puzzles for you, these sort of ways of describing logic is really helpful for that. And maybe that's what game you're going to write down in the future or something like that. This could be really useful for you. So implication, and just pretty much says if P then Q, that's what it really corresponds to in terms of more computer code. It corresponds to being either Q is correct, P is false. So Q is right or P is false, essentially what it boils down to. So that's the truth table. Truth table just tells you quite clearly what it is. So essentially what it boils down to is if Q is true, fantastic. If P is false, we don't really care what happens anymore. So P is false, who cares? But if P is true, then we must insist that Q is true. That's the key thing. So if P is true, Q must be true. If P is false, who cares?
Why is P1, Q0, why is that 0 then?
So if P is true, Q must be true. So you can say here, if P is true and Q is false, that's a problem. That means it's not working. So let's give an example where we might use this.
Okay, that makes sense.
Okay, so you got it. So in terms of maths, P might be the shape of a rectangle. Q is the diagonals are equal. It's a mathematical statement, which you may or may not remember from school. So, for that sort of thing, as soon as you say that, if it's a rectangle, it has to have equal diagonals. They can't, so you can't say, oh, it doesn't have equal diagonals anymore. So that's what I do. That's the truth. That's the truth table for implication. So it's logically equivalent to saying not P or Q, and you can write it in lots of different ways, but if P then Q, I guess is the simplest way. To give words, I just want to describe the two parts for it all. So in practice, we tend not to deal with a bunch of logic statements. We tend to deal with an English sentence, but it's useful just to, when you have an implication, I want you to be able to pull up two parts. So the two parts is the bit on the left of this implication is called the premise. Sometimes people use the word antecedent, which means the thing that comes before. So premise is what I like. And then the Q is the thing that comes from, I'll call it the conclusion, consequent, we use it in general. So premise and conclusion. So what I would like to do a little bit later is I've got an English sentence, so I'd like you to say, oh, that's the premise or premises in general, that's the conclusion. Just because we need to identify the parts to be able to do stuff with them. And we'll see some in practice in a second. We can talk about a double implication. That means P implies Q and Q implies P, both at the same time. There's lots of different ways of writing it down, but it's pretty much say they're equivalent to each other. A common mathematical way of writing it down is that last one here. That's saying P if and only if Q. If. Yeah. Or IFF for short. If. Yeah.
Could you go back one slide for a second, please? Thank you.
So in terms of there's lots of different alternate versions here, but the things I want you to take away is the definition. So premise, conclusion, and I want you to know the truth table for implication. You know the truth table, you pretty much understand what it's about. So, and in order to deal with it, to try to use the algebra properties of logic, if you just realise it is P Q or not P, that's a way of dealing with it as well. If you know that, then you probably do the truth table at the same time. So the next logical question I'll move on if it's okay, is just to say P implies Q and Q implies P, both at the same time. And the truth table again is the key thing. So either they are both true or false, both false. Other options we don't tolerate. So in that sense that P and Q are equivalent to each other. That's what we try to mean by the truth table. P is equivalent to Q.
Don't. I will stab you.
And I'm using these particular ones to try to talk about, want to prove stuff. So proofs really are just a bunch of implications one after the other, is how you often think about them. So when we write down that sort of stuff there, really said the top one step imply the next step, which imply the next one. So they're just a bunch of logical implications, is one way to think about what we did. You can just think about just do a bunch of steps and that's it. But that's where it comes from a philosophical point of view when I take that. Okay, so here's some terms. So what's a tautology? Read, I'm sure, but...
Did you say tortilla?
Tautology. What's a tautology?
I am. I did make inquiries about it when I walked in, so...
The study of water.
Oh, God.
I encourage you to read the slide.
A compound proposition is a tautology.
So tautology means always true.
That means like
Nothing.
David Waller doesn't shut the
Do you want to
lectures.
buy? Let's go outside right now.
So a green car is a car is a tautology because that's always true.
What if the brand is called Green?
What?
It's a green car. It's a.
What if it's an economical
It's
car?
a red green car.
What's a statement that's always false?
Sorry?
Well, so a tautology is something that's always true. What do you call something that's always false?
A fortology.
Or contradiction is the word for it.
Oh, that makes sense actually.
So contradiction is something that's always false. What do you call something which is sometimes true, sometimes false?
Maybe, I don't know.
Contingent.
It's called contingent.
That also makes sense.
So it depends upon what the variables are. So there's three words. So I'll often ask you, here's a logic statement, is it a tautology, a contradiction, or is it contingent? So which of the three is it? So it's one of those, it's always one of them. So tautology, always true, contradiction, always false, contingent, everything else. So it depends, essentially. So just... Yeah, so if you do the truth table for it, which is how now we're going to do in practice, there's a few ones and there's a few zeros, a bit of both. So a tautology would have ones the whole way through the truth table, and a contradiction would have always zeros. If you want to think of it that way. Okay. So here's a logic statement. This one says that P and Q implies Q. So I reckon this is a tautology, which is the same way of saying it's always true. P and Q always implies it. Okay, how are we going to prove it's a tautology?
Go through them.
Okay, so two options. One, you can use truth table, which we'll do in a second. Another option is to use the algebraic properties of logic to try to prove it. To show that if you convert it into logic statements, you can reduce it just down to just being true. They're the two different approaches. As this question's phrased, you could pick either. So which would you prefer to do? If you had to do it?
Truth table. Truth table. Just eat it.
I think I may eventually grow numb to that noise, but still.
Eats a lot.
So you got P and Q, the 0011.
That was running for this.
So what sort of intermediate stuff do we need to put in here?
Just P and Q.
So P and Q we definitely need. That's P and Q. Let's put the word "and" here to remind ourselves. So,
Oh, that's the relation. Oh, okay. I'm like,
okay, so definitely we need to know P and Q before we can do anything else. So that's one definitely key part.
We need to put in the up there, the P and Q arrow.
Not yet. We'll do that. So we want to, at the end of the day, we want to have a truth table for this as the last column. That's what we want to do. We don't know how many columns we need just yet.
do all the Q first. Because it's like, oh wait, no, it's not double. I have no idea.
Okay, so how about you just remind yourself by writing the truth table for the P and Q down on your piece of paper first. You all done that?
That would be 0001. Yeah.
That's a rigid.
Yep.
I don't mind the other way around. So.
Amazing.
Okay, yep. That's fine. Okay, so is everyone okay on that? On board with that? So now what we want to do is somehow get this implication thing down. And my suspicion is you may not. So you could do it directly. So if you just think what implication means, you could do it directly. The other option is you go, I'm not quite familiar with this implication yet, so you might want to do the other approach. So let's just write down some notes down the bottom here. We'll use different letters. So if you had A implies B, that's the same thing as saying that either B is true or A is not true. So they're the same sort of thing. And since you're more familiar with and, alls, and nots,
So then we have not
that might.
Q. So we put down a not Q as well. This looks complicated.
No, we don't, because you're just going to think through what it means. So in terms of what we got up here, that's the A, that's the B.
Oh.
And so the B here is Q, which is fine, we know that already.
Oh.
And what's the A in this case?
Yeah, something else.
P and Q. So if you want to take this approach to simplify it down, we need to know then, that tells me that we need to work out the not of P and Q, just so we can apply this sort of a statement here. Just so we can apply it directly. Does that make sense? Just because we understand that ands and alls, nots better, we'll just convert it into ands, alls, and nots. So therefore we need to know the not of the beginning part, the not of the premise, essentially. And so how do you convert the 0001 into the nots of that?
1110.
So just flip them around. So where you got zeros, put down ones, where you got ones, put down zeros. And so here, we really want to have P and Q implies Q. That's our last column. And in terms of what this, our translation at the bottom, that's the same as saying the conclusion is true or the premise is false. They're the same thing. And this last bottom one here, that's the one we're going to deal with from the truth tables directly. Does that make sense? So we've got our Q. Q's over here, it's fine. We've got OR, and we have our not. P and Q is this column here. So we're just taking the OR of those two columns, essentially. So two ones are labelled green, just taking the OR of them. So to work out this entry, that's really saying 0 or 1. So false or true, and that is?
Always true.
So it's true. True or true?
True.
False or true?
True.
And true or false?
True.
Do you see how I went through each of them one at a time? So instead of trying, I mean, you couldn't understand the implication directly and save one column in that truth table, which is actually okay. But since you're more familiar with the ones, I think that extra step, I believe, perhaps a bit more helpful for you. Yeah, well, so this is the truth table for the expression that we have that we want to consider. What does that truth table tell you? It's always true. And so something that's always true is called a tautology.
That's crazy.
So, has anyone heard the word? Has anyone actually used the word tautology in general English?
Never.
Like a car is a car because it's a car.
Well, a car will then not be a car.
What if it's a great car? Then we have
All Java names are kind of scratch.
Because it's
Really? From start this again?
Yeah.
Bump car's
Okay.
not a car, is he?
Yes.
This is still a car. Tautology. Yeah.
So things like
Don't judge that.
it's when you're a bit redundant in language. So giants are tall. It's a tautology.
Dwarfs are short.
And so in English, from an English point of view, some people are criticised from writing stuff which is clearly implied by just the first few words. So things like the giant is tall. You go, well, we're giant. It's not a giant.
Lecturers are smart.
That's a contingent.
Okay,
call
thanks.
Cameron?
Both days.
Okay.
Why did I? Someone.
Wow.
Wish we could.
So
Am I not coming to your classes last semester?
you can do the same sort of thing to other expressions. So I'll leave this I'll sort of one as practice. So this is a common sort of question. You'll get given an expression, and you have to work out if it's a tautology, a contradiction, or contingent. So that means work out the truth table in practice, and then go, well, what is it? And if you've got the truth table, it really is easy to see. If they're all ones, tautology. All zeros, contradiction, a bit of both, contingent.
So it has to be like 50-50 different contingent or
No.
any mix?
Any mix at all.
Okay, cool.
So contingent is if it's a random thing, it's probably going to be
It's like the
contingent.
weird Bronco. The other two are like, big, strong, the contingent's just there. It's a mix of both. Looking for
Okay,
Thanks.
skip this stuff. Okay. So I just want to talk. I think looking at the time I've got left, I think I might do this one example, and that will be it for the lecture, rather than trying to start something new.
Yes.
10 minutes.
The kindest person I've ever met.
He's like JK. You would come on detention, please.
Yeah, no.
I don't think you can do that. I
I can kick people out of class. The last time I did that was years ago.
Why did you? Why did you? What brought that around?
Someone decided to tip their contents of the bag and the person in front of them.
Oh, wow, that's rude.
Yeah, it is. They were apologetic straight away. They realised they were the mark.
What was in there, though?
Is it almost as bad as hindering?
If the other person had to leave the classroom and stuff, they got dumped on. So they got. So
Probably would have been worse with like a drink or something, though.
So I find that probably the people that probably would want to be really disruptive probably aren't here in the first place. So it's unlike in the classroom situation at school. So here, if you're going to be really disruptive, you're probably just not here. So thank you for coming, by the way. I do appreciate you coming.
Thank you for coming. Yeah.
Yeah.
Well, at least it's not as bad as Jim sometimes comes 10 minutes late.
Yeah,
It's just like, oh, sorry, I forgot I had class.
Even though
Wait,
I went to the wrong room.
Okay.
Yeah.
Oh, yeah, he's great for coming late.
Yeah, he is. He came like so many times.
Okay, let's finish this one off.
I had class.
You can when's about lectures in a second.
Oh, yes.
When it's not recording.
Yeah, there's a big recording behind me. So we can prove this. We can work out if this is a tautology, contingent, or contradiction using a truth table. You can also use the rules of logic. So how would I'll try to use the rules of logic to see if I can simplify it down. Give way of trying to simplify it down. So here I've got this expression. So using the rules of logic, I can see I've got a Q and in both those parts.
You have a P or not P.
So I would think to factorise that Q and bit out. Be one way to simplify it down before I go anywhere else. So what's left is P or not P. And the rules for that, because I'm factorising, that's the distributive property. We're going to give a name for it. So the next thing I want to do, guys, if that noise gets picked up by those microphones above you pretty well, so.
There's just like what's going on with that room.
No, I'm sure
I bet it will happen. So the P or not P looks like the best thing to try to simplify. So what's P or not P?
So P or not P is true.
So it's either one or the other. So T for true, 1 if you want to think of that way if you want to do, but true is what we've been writing down for the statements. So it's dealing with complements.
So Q and true is just Q.
Or negative, so the complement property. And then we have to do Q and true.
Which is just Q.
And that one there is the identity property. That's what I'm looking for. Again, you can look them up. I mean, I ran them off now, but you can just look them up. So that's the identity property. So we can see this expression simplifies down to just Q. So the question is that a tautology, contradiction, or contingent? Okay, well, it depends what Q is. So it depends. So therefore, must mean it's contingent. So it's certainly not always true. It's not always false. It depends what Q is. So contingent.
How embarrassing.
Do it again.
Kick camera out.
And it's saying truth tables would have been also worked there, of course, but you can show that's not the only way of approaching it. And that was not difficult. I would like to propose that is not a hard thing to do, on those sort of steps. So although at first glance that seems really daunting to try to take that approach, it need not be that bad. You don't have to balk at it at first glance. So thank you for listening most of the time.
Sorry.
Tautology, contradiction.
Discuss a little bit.
So what we'll do tomorrow, I'll look at proofs tomorrow. Just looking at some implications of this logic sort of stuff. If you have any questions about the material, can you guys be shot quiet just for a little bit longer?
I'm like, whoa.
Okay, I will do proofs tomorrow, which is the flow on from this. The assignments are all up there. The assignment 1, the first got a few questions. They're not all the same length. Question 1 is all about the set stuff. You can do all of that now. Section 2, question 2 is about logic. So what we've just been finishing just up then. And the third question is about proofs, which I'll do in the next lecture. But you can do the first 2 questions of that assignment. Yeah, there'll proofs involved in that sort of stuff, yes. So basically everything I've covered so far in lectures corresponds to questions 1 and 2 of that assignment 1. So, and that improves some proofs already, as you've noticed. But I want to look at different proofs type in a second. So, all of what we've done so far are called direct proofs. I want to think of other ways of proving it. Alright, so don't leave the assignment to the last moment. You do you often do a crappy job that way. So start it now.
Leave it till after I've started.